So this is the review for the Unit 2 quest on atomic naming, matter, atomic structure, and percent. So this is the Unit 2 quest review on naming compounds, atomic structure, average atomic mass, and properties of matter. This is the Unit 2 quest review. Name the following compound, CuNO3. A couple things you need to look at here. First of all, since this is a couple things to look at here. First, you have a metal. That means this is going to be an ionic compound. And copper is a transition metal, which means it is most likely to have more than one type of ion. There are some transition metals that can only form one ion. So we are going to need to indicate in the name which particular species of copper ion we have here. We're going to do that with the Roman numerals in the name. Now that we know that, we have to figure out which Roman numeral to use. To do that, we're going to take a look at NO3. NO3 is the polyatomic ion nitrate, and nitrate has a charge of -1, which means that copper must have a total charge of +1, and since there's only one copper, that copper is a +1 ion, which means that we need to find the one Roman numeral, so either B or C, and since this is NO3, it's nitrate, so that tells me that we're going to be using copper 1 nitrate as our name. Number 2, which compound matches the name Rb2CO3? Okay, so again, first thing, we've got a metal, it's an ionic compound. However, in this case, rubidium is not a transition metal, which means we do not need a Roman numeral in the name. So that eliminates those two right off the bat. And then the next thing you need to do is take a look at the polyatomic ion at the end. CO3 is called carbonate. So that tells you that we've got rubidium carbonate here. Acetate is a different polyatomic ion with carbon, hydrogen, and oxygen. Number 3, which name matches the following compound? So here we have nitrogen and fluorine. So we have two nonmetals, which means this is a molecular compound. Molecular compounds, or covalent compounds, we need to indicate the number of atoms by using prefixes. Because molecular compounds, nonmetals can often combine in more than one ratio. So we use, and there's no charge to base it on, so we need to use prefixes. So N3, 3 has the prefix tri, and F7, 7 has the prefix hepta. So that means we are looking at trinitrogen heptafluoride. Just remember a couple of things. If there's no subscript on the first element, you do not need to put a prefix on it, but you always need to put a prefix on the second element. Which of the following compounds is carbonic acid? Okay, so acids are compounds that have hydrogen as the first part of the compound, and then in this case where we're talking about an acid, all of these have oxygen. So these are polyatomic ions that all have oxygen in them. So we need to go back and figure out which polyatomic ion would end up being named carbonic. So the two possibilities are, if you have a polyatomic ion that ends in ATE, then you would change the ending to IC, or IC, in the naming of the acid. If you have a polyatomic ion, for example, that is ite, you change it to OUS. Okay, so in this case, carbonic, if we work backwards, means that the suffix was carbonate, and carbonate is CO3, and we need two hydrogens because CO3 is a polyatomic ion with a charge of -2, which is why we can't use this one, because HCO3 would not match up with the charges. And then the other choices are just, none of those are carbonate. If the same mass of oxygen combines with 2.5 grams of X to form compound 1, and 6.25 grams of X to form compound 2, which are the possible formulas for these two compounds? Well, you need to look at the ratio, because we're talking about the same amount of oxygen in both. So if we find the ratio of X in the two compounds, we've got 6.25 in one and 2.5 in the other. So there's a ratio of 2.5x in these two compounds compared to the oxygen. Keeping in mind that you can't have a fraction in your subscripts, there's no way that any of these choices come out to 2.5 times x, right? Because 8 is not 2.5 times 3, 9 is not 2.5 times 5, 4 is not 2.5 times 2. So the only one that's left is B, because 4 times 2.5 is 10. You've got the same O2 in both, so that gives you the two formulas for the compounds. If 4 liters of A combines with 2 liters of B, we know that there are 2 times the number of A molecules. And how do we know that? We know that because of Avogadro's law, which says that if you have equal volumes of gas at equal temperature and pressure, then you have an equal number of particles or molecules in both containers. So since we have twice as much A as B in terms of volume, and assuming that we have the same temperature and pressure, that means there are twice as many molecules or particles of A in that container as there are in the one for B. Which is not true of the following symbol. Potassium 40 with a charge of +1. The atom contains 19 protons. No, it absolutely does, because it's potassium. No matter what, it's got 19 protons. It contains 21 neutrons. That is true, because 19 plus 21 gives us this number up here, the number 40, the mass number. It contains 20 electrons. Well, if it had 20 electrons and 19 protons, it would actually have a charge of 1 minus. Since it has a charge of 1 plus, it's actually got 18 electrons to 19 protons. That's how we end up with 1 plus. And atomic number 19 is always potassium, so that's not true either. Or that's true, which is not the correct answer. Who conducted the gold foil experiment? Well, Dalton came up with the early version of what we would call modern atomic theory. J.J. Thomson, he did the cathode ray tube experiment and came up with the plum pudding model, so that wasn't him. Rutherford is actually the guy who did the gold foil experiment, and Millikan did the oil drop experiment. You kind of need to know who these people were and what their contributions were. So Dalton, Thomson, Rutherford, Millikan. Know what their models were, know what their experiments were, if that applies, like Thomson, Rutherford, and Millikan all had specific experiments attributed to them. Thomson discovered the electron, Rutherford came up with the nuclear model. He was the first to propose the idea of protons and the nucleus in an atom. And Millikan's oil drop experiment determined the mass of an electron, which was the first evidence that there was particles smaller than an atom. So know who these guys are, know what the nuclear model looks like, know what the plum pudding model looks like, and who each of these guys were and what they contributed. What did the oil drop experiment discover? We just mentioned this. Okay, the mass of an electron was discovered as a result of the oil drop experiment. The negative nature of electrons was discovered in the cathode ray tube experiment. The nucleus was discovered in the gold foil experiment. The mass of a proton was not really discovered in any of these experiments. An element Z has two isotopes. Z27 and Z28 are 35 and 65% abundant respectively. Calculate the average atomic mass. So what you need to do here with the average atomic mass is take the mass of the first isotope multiplied by its percent abundance as a decimal. So it's 27 times 0.35, 28 times 0.65, and we get 9.45 for the first one and 18.2 for the second one. We add those together. So these two numbers, the 9.45 and the 18.2, are called the mass contributions for each isotope. And then at the end, you simply add all the mass contributions together, and you get a mass of 27.65, which we can round to 27.7. Sorry, I said 26, but 27.65 rounds to 27.7. And that makes sense because the more abundant isotope is 28, so it makes sense that the average would be closer to that number than it would be to 27. Number 13, if an atom has 11 protons, 12 neutrons, and 10 electrons, the atom is not neon. Neon would have 10 protons. It's atomic number 10. The atom is positive, yes, because you have more protons than electrons, so it's a positive ion. Mass of 21? No, this would actually have a mass of 23, 11 plus 12, and atomic number is based on the number of protons, so it's definitely not atomic number 12. All right, so one of the three isotopes of X has a mass of 21%, an abundance of 21%. The other two isotopes are 20 and 21. How can you figure out their percent abundances if the average atomic mass is 21.4? Okay, so we went over this a little bit in class, but here's what you need to do. First, you calculate the mass contribution of isotope 23. We can do that. Okay, 23 times 0.21 is 4.83. So that's the mass contribution of the first isotope, which is the one we know. What's left in terms of the average atomic mass, 21.4 minus 4.83 is 16.57. So that's the mass that we need to account for with these other two isotopes. The other thing that we know, that we can use, is the fact that we know that all three isotopes have to add up to a total percentage of 100, which means if the first isotope is 21, then the other two have to combine to make up the other 79%. Okay, that's just a fact because it's a percentage. So we can use that to say that the mass of isotope 20 times X plus the mass of isotope 21 times 0.79 minus X, because the two have to combine to 0.79, equals the amount of mass that we're looking for, 16.57. So if we solve that equation, we end up with X equals 0.02, which would be 2%. So according to this, the percent abundance of isotope 20 is 2%, which would make the percent abundance of isotope 21 77%. And if you do that out, if you do 20 times 0.02, you end up with, plus 21 times 0.77, you get 16.57 AMU, which is the number we're looking for. If you switch the percentages around, it doesn't come out to 16.57, so that's how we know it goes this way. Okay, last one. This was not in the packet that you got in class, but there were similar problems to this in the book. Actually, I think these two problems were in the book. We talked about them in class, and there is a problem like this on the test, so I wanted to add it to the review. So, write out the simplest balance equations for the following. So if we're basing, remember that volumes can be used, if we have 6 volumes of A, that means we have 6 times as many atoms or molecules of A as we do B. And the 4 volumes of product means that there's going to be 4 molecules of product for every 6A plus 1B. So the way to solve these problems is to sort of find the least common multiple of all the numbers involved. Well, 6, 1, and 4, of course, all go into 12. So if I have 6A, but I need 12 atoms of A, that means A must be a diatomic molecule with subscript of 2. And if I have 1 volume of B, well, that means that B so So in order to solve these, you need to use a least common multiple for the different compounds or the different substances. The 1 for B, since it's a 1, I can make B any type of molecule I want. I'm going to use subscripts and what are called coefficients to work out this balanced equation. I can make the subscript on B anything I want, so I'm just going to focus on the A and the product. Well, the least common multiple of those two numbers is 12. So if I need 6 volumes of A to give me 12 A's, then each one of those molecules has to have 2 atoms in it. And then if I need 4 volumes of product, I can have 3 in each molecule. And then if I have 1 volume of B, 4, then you can combine these in a 3-to-1 ratio, and you would get 4 volumes of product. So the same thing on the bottom one, 3 A's plus 2 C's produce 6 AC. Now what's the ratio? Well, since they all both go into 6, 3 and 2 both go into 6, I can make this a 2, I can make this a 3, and then I would get, when you combine those, there's 6 A's and 6 C's on the left. And if I have 6 molecules of AC on the right, then that would give me 6 atoms of A and 6 atoms of C on both sides. So that's called a balanced equation, because you have the same number of atoms on both sides, and you can use least common multiples and just count up the different combinations so that you have the same total number of atoms on both sides for all the elements involved. Okay, so we'll be starting, we'll have the test tomorrow, and good luck. Okay, last problem. We need to find the percentage of the mixture here that is made of hydrate B, and in order to do that, we're going to have to determine the percent of water in each hydrate and in the mixture. That's the first step, and then we're going to use that information to determine how much of the mixture is made of each hydrate. So the first thing is hydrate A is a total of 7.5 grams, and then once the water is driven off, there's 5.874 grams remaining, which means that 1.626 grams was water. And then if we divide that by the original amount of 7.5, it tells us that hydrate A, I'll put this over here, hydrate A is 21.68% water. Hydrate B starts out at 6.20, ends up at 3.383, which means it was 2.817 grams of water out of 6.20 total grams. Work that out, and we end up with 45.43%. And then the mix starts out at 6.75. After the water is driven away, it's 4.59, which means that there was 2.16 grams of water in the 6.75 grams that you started with. So the mix has a water content of 32%. Okay, so now we know how much water there was in each hydrate and how much water there is in the mixture. So we're going to use those in an equation to calculate the percentage of the mixture that was each hydrate. So we know that the mix is 32%, so I'm going to convert that to a decimal. 0.32 is water. That 0.32 is made up of hydrate A, which is 21.68% water, and some percentage of the mixture is made of hydrate A. So I'm going to call that X. Actually, you know what? Here, let's do this. Let's call it A. Okay, times A. And then the rest of the mixture is made up of the hydrate B,
which is 45.43% water, and the amount of the mixture that's hydrate B is 1 minus A, because A and B have to add up to 100% of the mixture, because we're assuming those are the only two things here. So once we work that out, we end up with 0.32 equals 0.2168A plus 0.4543 minus 0.4543A. And once we solve all of that around, we end up with x equals, or A rather, equals 0.5654 equals A. So that means that the mix was 56.54% A. And that means that 43.46% of the mixture was B. Okay, so you need to find the percentage of each hydrate that's water, find the percent of the mixture that's water, and then use the total as the percent of water in the mixture, and then each percentage of the hydrates contributes to 100% of that percentage. So it's a lot of percentages going on, but that's how it works.